my colleague and I, we've gonna explore a bit about LLMs, so very hot topic of these days. And of course, we need to a bit shift toward transportation. So we wanna also explore a bit how we can use LLMs in a specific transportation. But to start, is anybody in this room that they are not using ChatGPT for their daily tasks? Perfect.
The question is, do I use it for my daily tasks? Answer is no.
Okay. So better it's maybe to ask if you're using ChatGPT, for what tasks are you using it? Good. Any other things you use for great pictures? Nice. Perfect.
Plans.
For plants. Yeah, that's very good. They're doing great, right? I mean, and it is also going a very hot discussions everywhere that you go that, oh, how these LLMs are going to take us. But let's, just to start, to have a very warm-up game. Let's play around a bit with ChatGPT if you have it on your phones or your laptops. And at the same time, ask this question from ChatGPT. So, how many countries share a land border with the Netherlands? And I would like maybe our Dutch colleagues in the class also maybe give it this answer. And then you can also check with ChatGPT. So, how many countries share a land border with the Netherlands?
Three.
Good. But then ask ChatGPT. Interesting, right? It says Netherlands sharing a land border with two countries, Germany, today is Belgium, and it is very happy with the answer. It says, yeah, from the North Sea there's no border, so two. But actually it's not two, right? If you know so far or not, maybe. So the Netherlands is also sharing a land border with France. So in Saint Martin Island. So actually, Netherlands is sharing land border with three countries, not two. I also played a bit with more ChatGPT that, hey, you're doing a mistake. There is also a border with France. So France was a keyword that I added to the information that I put before. And it says, oh yeah, you're right. Yeah, it is three. So, and it explained, now it found it that, okay, it's with Saint Martin in France. Now we know also that Netherlands is actually sharing a land border with three countries. But what is the point here? I want to mention that ChatGPT knows a lot. Of course, we have explored this. It knows a lot. But their information still can be incomplete and even incorrect. So the answer that it gave us in the beginning, two countries, it was not wrong, but it was not complete. So if I was not familiar with the country, was not familiar with the geography, and then I was asking, okay, how many countries are sharing a land border with the Netherlands, I would have come to something not complete. So today, in this session, we are planning to first, in the first part of the lecture, to introduce a bit about LLM. The most important thing about these technologies is to understand what is going on behind. So to be able, when we are using it, to be able to use them a bit more wisely. So we will go through what are LLMs. So by the end of this session, we are expecting each other to give an answer, to tell us what are LLMs briefly, what are the main components of an LLM, and then what are the challenges at the moment and concerns about using LLMs. And of course, we want to shift this perspective, so the more technology perspective of LLMs, to the transportation and to see how far LLMs are affecting transportation domain as well. So we're going to see some examples of LLMs in transportation specifically. And then we're going to have a hands-on practice using LLMs and specifically transformers for predicting trajectories. And that's going to be about an example of how LLMs are also getting into transportation domain. So let's start with introducing the LLM. So first of all, it's a huge area, of course, but the most important thing is, okay, do not panic. It's not really something very extraordinary. Let's say the autocomplete and autocorrection feature on your cell phones that now you are used to it for a while, for years, it can be called as a very little cousins of GPTs. So you're already using this system, let's say this framework, for a long time. But what is exactly making these models a bit more specific, more interesting is like they are really large because they are trained on a massive data set and they have billions of parameters. Briefly back to the history, so LLMs actually, let's say, started because of introducing transformers. So the idea started from 2017. So it was not something new, and LLMs are actually putting pieces of puzzles together. But it started from 2017 with introducing the transformers idea. And as you see, different language models have been developed in years. We mainly hear about GPT and ChatGPT, which was developed in end of 2022. And the most recent one, the DeepSeek, that was in the beginning of this year. Let's understand when we are talking about LLMs, where are we standing in an AI field? We are standing in a deep learning area because the main foundation of LLMs is using deep neural networks. Deep learning is like an engine that you can use this engine to empower a specific vehicle or system. So you have this concept, but now specifically we are using that engine for a specific task, which is understanding and dealing with all the complexities for human languages. So this is a specific case of deep learning. And about generative AI, which we covered all this stuff yesterday actually. So they are part of generative AI, so they are generating content, but it's specifically text. So they are also somehow part of generative AI field. In one sentence, very briefly, LLMs are just advanced AI systems that are built on deep neural networks that can process, analyze, and generate human-like text. There are 4 features I want to emphasize here that what is exactly making LLMs a bit more, now these days, a very hot topic. The first part is they have a part in their architecture that they are converting massive text to the giant matrix of floating point. So, which they call it tokenization and embedding. So this is the very first part of the architecture. So whatever the text you give to the model, it gives a value, numbers to it. We will go to the steps next slide. They have billions of parameters. We always say about billions of parameters, but let's get some ideas of what these billions of parameters really feels like. So for example, GPT-3 has 175 billion parameters. So the model needed to train over 175 billion parameters, which is comparable to the order of the number of synapses in a mouse brain. The another thing that making LLMs very interesting these days is the attention mechanism, transformers, which we said is actually introduced in 2017. And it is actually the main part that is making LLMs a bit more specific. So they have this mechanism that they try to direct the attention of the model to the most important part of the model. And then finally, the training and resources is a very, very complex part because the training of an LLM model is the cost is very mind-blowing. For example, to get an idea about numbers, training GPT-4 which it had 13 trillion training tokens. It is estimated to over have $100 million, so the cost was quite high. And training was taking like 100 days, which was around using 50 gigawatt hour training power for training only one single one. And which brings another discussion about LLMs, that they are not really sustainable approaches. Now let's just take a look at the very simplified architecture of LLMs. It's good to get an idea in each step what is going on. So we're gonna have tokenization, we have embedding layer, transformers, and then a full layer. But what do we mean by tokenization? So in this part, whatever the text that you give to the model, I will just give a very simple example so we can go step by step together. So it says this is a trail course for AI in traffic. In this part, you will create chunks of, you make this to the chunks. But what is the length of these chunks? No matter. It can be word, it can be character, it can be any variant sequence of letters or characters. So here, for example, I just did it for, let's say, our tokens here are just words. In the embedding layer, a vector of numbers gonna be assigned to each token. Randomly numbers, but they have, of course, a concept, an algorithm behind that. I mean, the whole vector has a meaning. It's like assigning your word a vector of number that is also putting your word in an n-dimensional area. And for each of these words, we're gonna have that vector. Next step, and the most actually novelty of LLMs was transformers, so the attention mechanism. So what was it before? I mean, when this idea was not introduced, how was it done? So this idea of attention is coming from the 2017. So it was people, engineers in Google, that they come up with this idea that attention is all you need. That is a very famous paper that everywhere they talk about it. But the concept is they are shifting your attention to the most important part of the text. It's like, for example, you are driving in an area, and then it's like you are using Waze or any navigation apps. So these navigation apps is trying to somehow switch your attention to some areas that are less congested. So they are somehow leading you to the areas that are more interesting. How was it before? So before, when they were analyzing the text, they were dealing with those tokens and those embeddings with in order. So it was this, and then this next letter, next token, next token. But what transformers are doing, they are dealing with the whole text at once. So the whole sentence, this is a trail course for AI course, at once gonna be analyzed. So what does it mean? So transformers do not read the text from the start to the finish, but then they soak the whole text all at once. This gives the purpose for this is it gives these numbers a chance to somehow collaborate to each other. So they can somehow give some insights to each other, which exactly this point, if we talk about trail, if we usually say trail, and you Google, for example, an image for trail, you may have a trail for running or for biking, but because we are reading the whole text at once, we come up with another picture because it's trail for AI in traffic. And then the final step is the feed-forward capacity, which is actually somehow the deep learning method behind that this sequence of numbers gonna be processed in a feed-forwarding mechanism. The task for LLM is predicting the probable next word. So this is a trail course for AI in traffic. That was the input. So in this course, we learned to use AI in. So now is a turn to predict this word. How is it doing it? So after all those steps that we went through, so it was a feed forwarding and then transform. Then this feed forwarding is repeating. It comes up to the new vector of numbers. And this vector of numbers is giving the probability of possible words. It can be transportation, mobility, flow, and you see the rate is going down. So it's have a list of words that are possible. And now this is another algorithm that we need to come up with some idea, okay, how should we pick the word? Which they have different sampling methods. For example, you can be deterministic with, for example, greedy. In greedy, they just pick the highest number. So transportation has the higher value, let's pick transportation. Or in beam search still is a deterministic approach, but it sees the series of the next word as well. So it goes to the the second or third words also, and then it calculates the probabilities. It picks the higher one, and then goes to the next word. And then there are probabilistic approaches as well, right? For like top K sampling. What it does is say, okay, I have this probability of words. I will go, for example, for the third most probable, and I will randomly pick one of these, my sample. So that was the algorithm overall here. Still, we have this challenge with LLMs that we see there are some fake information. They have problems with putting words or some, for example, citations in your text that are not really existing, that the new idea of RAG was introduced. So what is RAG is actually doing is a simplified thing is an add-on to the LLM model. Is like giving a navigation or a GPS to that driver. So they have a somehow real-time estimation of traffic situation also on the way. So RAG is actually helping you to add some information to the model to make your generated text a bit more realistic, more factual, based on the real-time sources. So RAG stands for retrieval, which means that it asks questions and it searches through a new source of information. They are augmented, so because now you have a better source of information, and then they generate the text. So it simplifies, like they have a new data set that is more, let's say, more real-time, more based on fact, and then this text generation is based on that data set. Should we be happy that, okay, LLMs are good enough? Yes, using RAG as an add-on on LLMs, it's helping us to reduce the bias and hallucination that we see in the models, and the outputs are now a bit more factual, but this hallucination still happens because it's going again to that data set itself can also have some irrelevant or low quality information. The bias is still there, because if your training data set is still biased, so you have still this bias in your training, and then the bias is also remains because that external knowledge that you are also getting access to can be also biased. So in summary, what should we do? First of all, when you're using LLMs, be careful about the quality of retrieved data. So the quality of data that is there is important. All the time consider that there should be a bias in your results. So always consider bias detection and mitigation strategies. And important part is also having a human judgment and supervision is still a need for whole this process. And a new idea, maybe you can also think of creating your knowledge graph. As I said, the RAG is going to get an access to a new knowledge, to a new data set that is more reliable, that is more real-time. So you can also create your knowledge graph based on the domain that you are working in, that your RAG is also getting access to that data set for text generation. So far, we just briefly went through LLM architecture, just some terminology that is used in LLM, but of course we need to shift a bit toward transportation. How LLMs now are being used in transportation. Of course, there are multiple sources that you can explore if you are interested. So there are literature papers that they are just having a review over all the applications of LLMs, and specifically in transportation. And also there is an article in NM magazine that is authored by our colleagues in Transport and Planning in TU Delft that you can also take a look into, that they go also over the different applications of LLMs in transportations and also the weaknesses and the problems that might be with LLMs. But just briefly about some applications of LLMs. For example, they're using at the moment LLMs for traffic signal optimizations. So they are using it for having scenarios. So there is a LLM language, LLM scenario that they are bringing some safety scenarios. They are using it for the geospatial mobility modeling. They are using it for multimodal demand prediction, and is also being used for crash safety analysis. These crash LLMs, they are analyzing all the crash reports, and based on those crash reports, they are predicting the severity of accidents. So these are just some examples, and there are much more in the literature, and some also real-world examples. And of course, there will be more. Which with this session, we're gonna also have a real application. We're gonna have a hands-on practice for using LLMs in predicting trajectories, which Weiming will go through.
Yeah. So we are not going to just directly apply LLM for the prediction methods, but we are focusing on the transformer, which is the most important part in language model. So what is the mobility prediction? So you can imagine in autonomous driving, the vehicle need to predict the pedestrian, how they move in advance, so that they can like make some adjustment to the movement pattern to avoid the pedestrian. This is in a more micro scale, but in a more larger scale, or maybe in an urban city, we can also predict, or let's say simulate the trajectory of the human mobility. What is the benefit of that? We can use this kind of simulated trajectories of the individual to like make some transportation modeling, which can be benefit for in the downstream simulation task. So how can we translate the transformers into such kind of trajectory prediction, or let's say trajectory generation problem? So we can just treat the trajectory prediction as a sequence-to-sequence problem. So basically, a sequence of trajectory. You can just treat it like a sequence of words. Each of the words can be corresponding to the coordination of the pedestrian. Let's say, for example, for this time step, you are in A, and next time step, you are in B. And this location will be tokenized and feed into the transformer. And of course, trajectory is sequential, and it has long-term and short-term patterns. The transformer can be really good to handle this because there's an attention mechanism inside. As introduced by Masha, attention can capture both short-term and also in the long-term characteristic in the long sequence. And also, some of the spatial features in the trajectories can be directly tokenized, or let's say, to embed it into high-dimensional features, which can be directly inputted into the transformers. And so usually the trajectory status is quite large. In the later on hands-on practice, we will see there's in total 20,000 records of the user's individual's trajectory. But this is always just a small data set. In larger data set, there's also 150,000 users' trajectory. So it's quite a large data set. So we can utilize the scalability of transformer to train on such kind of a huge data set. And we hopefully can see some of the emerging intelligence from the transformer. The last one is trajectory is usually stochastic, which is quite suitable for this kind of task. For example, we want to generate the sequence of the trajectory, which is a more statistical process, not a deterministic process. And so, do you see any advantage of the transformer over LSTM? But we would put this question later after our hands-on practice. Okay, so yeah. So basically, we translate location into words, and trajectories is the sentence. And what we're going to do next is to predict the next move given the past trajectories. So Here's an example. So this is like a coordinates of the coordinates of the pedestrian, and we use these coordinates and then tokenize it as such as some kind of words like x 45 and y 120. And then we can also incorporate other temporal features like the time of the day and the day of the week. All of this can be tokenized and embedded into the inputs. So of course, if we have other special tokens, because we want to mimic the trajectories into kinds of language. So we need some kinds of special tokens to inform the models that when we need to start to predict and when we need to stop. So now each trajectory we can translate into a sort of a sentence. And in the transformer, there's two parts. One is the encoder, the other one is decoder. Basically, encoder use the past trajectory as input and feed it into the decoder. The decoder uses this information to predict in the future steps. So just like what we learned in the LSTM, the legs, you can treat the legs as the encoder and the horizon as the decoder. Let's dive into the hands-on practice now, but first of all, I will give you some introduction of the dataset we are going to use. This city is divided into 40,000 grids, and each of this grid is like 500 meters times 500 meters large. And yeah, and the total time span of the trajectories of the individual is 75 days, and it's discretized into every 30 minutes. So each time step, each interval is 30 minutes. So if you, so now you can, if you have the access to the slides, maybe you can start to click on this link, and then you can run the first block of code, which to visualize how does the data look like. So basically, we have the features of the ID of the user, and day, and also time of the week, and the location. We also add some other features like the cluster of the users based on the frequency they visit a place. Also, the time difference between his current step to the last steps, because the sequence is not continuous, quite continuous. Some of it is like 30 minutes, but some of it maybe is a few days. So we need this kind of information to know how difference is between each time step, and this time difference is encoded also with categorical features. The next block you can visualize the data. Basically, is all the data points in the city scale, and also how often the people visit each location with this heat map. And the third graph is the trajectory of one individual. Yes, this is the tokenization process I introduced before. We tokenize the coordinates of the pedestrians. And in total, there are 404 tokens, because there are 200 tokens for x-axis and 200 tokens for y-axis, and also including 4 spatial tokens, so it's 404. In this block, it introduced how does the inputs of the model looks like. So basically, it's a sequence of the location plus the time features. The decoder has to know when it starts to predict, so we need to incorporate a start token also. And in the targets, we have the end token for the last words in the sequence to give the signal for the transformer to know when it should stop. So in the training process, pretty much the same as what we learned in the LSTM. We split based on the time. The first 60 days used for training, and the last 7 day for next 7 day for validation and last 7 day for the testing. We are going to predict the trajectory with different inference method we introduced. There's greedy, there's sampling, there's beam search. So you can choose each of these methods and see how they behave in the prediction. So you need to first run this block of code to get all the helper function. So in this block of code, we can set the encoder steps, which is we learned in the LSTM. There's a leg we can choose. So this contains all the contextual information. For example, when you chat with a chatbot, you have to type what kind of task and what kind of prompt you need in advance. Then this basically is the inputs of the encoder. So we all know that if the context is longer enough, the performance usually is better. So you can try with a shorter encoder steps and also longest encoder steps to see how does the model performs. So in this example, there's 20 users choose. You can also choose more samples with just modify this value. And it load the data. And here you can choose whatever inference methods you want to see. Here is a sampling, and we use the top case sampling, so we only choose the first 10 candidates and to sample among these 10 candidates to predict the next location. And for the beam search, there's a parameter we can tune, is the beam width. So basically, if it is set as 5, it means that in the final prediction there will be 5 predicted sequence, and the model will choose the best, or let's say the most likely sequence among those 5 sequences. And the temperature is related to the sampling methods. So I'm not sure whether when you use ChatGPT, it was before you can turn this temperature parameter. If you turn it to be lower, the model will be more certain, and if you turn it bigger, the model will be more creative and more generate some more statistic patterns. You can try with turning with these parameters and to see how does the models perform. So now it's 0.8, and the model you can see the prediction actually can coverage most of the ground truth if it's the green line. And if we turn these parameters to be like 0.3, yes, now we have lowered down the temperature, and then you can see the predicted trajectories is becoming more certain, and it cannot coverage most of the variance of the ground truth actually, which can be interpreted when we use the ChatGPT. If we turn the temperature higher, then it will be more creative. You can play around yourself, but for the last one is the visualization of the tension. Basically, it visualizes the importance of the models, how the models perceive the importance of each of the tokens. So in the y-axis is the input of the decoder, and the x-axis is the input of the encoder. So we can see the start tokens first, it emphasizes on the first token is x21, and which means that this token has more information, and in the prediction it uses these tokens more than the other tokens. So we can see that the x token actually emphasizes more value on the y coordinates, which makes sense because in the sequence usually is we first predict x and then predict y. So when the current token is x, it has to predict y in the next step. Okay, and lastly, just try to think of which kind of features you can incorporate into your model to make the prediction more reliable, and also think about what is the advantage of the transformer, and is there other traditional machine learning methods can be used for this problem? Okay.
So what we were expecting to learn The first one is, okay, LLMs refer to large general purpose language models that can be pre-trained and then for specific purposes. If we do not learn, we will not live.
Used?
Yeah, somehow tested. So, but the terminology is fine-tuned. So usually what we can use from LLMs, we are using the LLM model, but we fine-tune the model for a specific domain. So we can have a fine-tuned LLM model for transportation domain. So the second one, through which process in LLM, we compress all the input data into a giant matrix of floating point numbers. Yes, perfect. So through the embedding or tokenization, we did this. Then through which process we are giving attention to the most important part of a sentence? Transformers, yeah, or attention mechanism. So in the transformers, the transformers actually process all words at once, while humans read sequentially and shift attention to more important tokens. And they do not memorize text, so LLMs do not memorize text, otherwise they learn patterns of language. This is actually something important about LLMs. You remember the chart that we show about the numbers like transportation 90%, mobility like 10. So it's exactly, so it's learning the probabilistic pattern of the language. And we showcase the transformers are a good approach to predict trajectories because traditional models like RNN, LSTM cannot. What was the feature in transformers that was very interesting to explore for predicting trajectories? It was because they are able to handle longer sequential data, and they had this mechanism to capture long-term patterns. Just because it's a hot topic, LLMs, everybody, somehow we are using it in our daily life. Just some quick nudges, just to remember. They are still sometimes hallucinate word citation and so on. Just so be cautious about this. They generate words that do not really exist. So it's like when Google Maps leads you to the feed path that is not existing. So be cautious whenever you are using LLMs. They do code. We are using for coding quite a lot. They are doing great actually for coding. But remember, they're not understanding the reasons and needs for that piece of code or piece of software or application that you are using that code for. So they are not understanding the concept. But they are great in coding. They are like parrots. They are mimicking the patterns. They are doing great in this, but it's still they're not understanding. Training part of LLMs is a very cost not efficient part of LLM. So, but once it's trained, it can easily run. You can easily use it later. Don't forget, although they are doing great, they are still doing text prediction. They are not really having internal logic. And finally, still they can reflect bias. So because of that data set that you are putting inside, they can reflect bias.